The plan cache is a sort of structure within SQE that allows us to take the result of optimization, which is a plan or an access plan, that's the full name, and it allows us to store that access plan for future use. The idea is that optimization is really, really expensive, right? A query might take a few milliseconds to optimize, but then might run in a few milliseconds as well. But we only have to optimize once if we can cache it, and we can rerun that plan millions of times without ever needing to get a new plan. So we're saving lots and lots of time, lots of memory, that sort of thing. If you go to the SQL Performance Center, you'll see a lot of really awesome stats about the plan cache. And I just want to highlight a few things. I also saw a comment in the chat there about some bad SQL practices, and one of them you can investigate here. So another good sort of mention. I'll make the text bigger. For those that don't know, maybe this will be worth the price of admission. Control plus and control minus scales the fields in ACS. Not many folks know that. Maybe it's only useful for me because I'm sharing my screen a lot with ACS, but might be useful for you folks too. Anyway, the first thing to note up top is the time of summary and creation time. One really important concept is that the plan cache is resident in memory. So when you IPL, the plan cache disappears. I have had people come up and ask me, hey, can you improve the plan cache so that it stays on a hard disk, right? We don't have to clear it between IPLs and you can just pick up where we left off. In theory, yes, we could do that, but it introduces a lot of engineering problems on our end. For example, if you're to save off your plan cache and you bring this plan along from one release to the other, we have to support plans from multiple releases, which gets really messy. And at that point, you might be able to string along plans from multiple releases or bring a plan from, one system to another by, changing a file or that sort of thing. Really messy. We're not investigating that now, so don't get your hopes up too far. But other parts of the plan cache, here's this hit ratio. So there's this concept of wanting to store almost everything, but not everything on your system. And if we were to store every single plan, you'd see so much memory usage. It'd be ridiculous. And we can't possibly store everything. Besides the memory cost of the plan itself, there's also all of the temporary data structures associated with the plan, which don't necessarily show up as part of the plan cache size, which is right there, unit megabyte, right? So about 6 gigs there. It doesn't include all of the temporary runtime objects, which can get really, really expensive too. In fact, if you scroll down there, you can see the number of temporary objects along with the size of those. So in this case, we've got 4 extra gigs, and that can get bigger and bigger if you've got a lot of queries. My last note here, then I'll quit sharing my screen for a little bit. We can go back to Charlie's questions here. Someone asked about bad query sort of paradigms, things to avoid. One of them is QTemp plans. And we do have a tracker in the plan cache to highlight that. When you see a large number of QTemp plans, it generally means that performance might not be as good as it possibly could be. The reason is that QTemp is unique for every single job that runs, right? So job A's QTemp is different from job B's. That's the point of QTemp. When you use a query when you run a query that uses a QTemp scoped table or index or what have you, we can't reuse that plan for other jobs that are using that same query. So if you have multiple jobs running the exact same query, but they're referencing a single QTemp object, we cannot reuse that plan at all. And that does a few things. One, we're going to optimize once for every single job that's running that query, which if you have tens of thousands of jobs running this over the course of maybe a day, that gets really expensive and very wasteful. Another thing is that we aren't able to properly gather statistics about your data. This gets a little complicated, but essentially, if we have a permanent structure, like an index or a table, we can collect statistics about that. And by we, I mean the optimizer. And we can make better informed optimization decisions with those stats. If you're using QTemp, we're just kind of slopping the data in there. And, well, we can't get stats because we don't really have time. And we also just preferentially don't investigate QTemp stuff as frequently as we do other things because it's temporary. There's no point in us wasting a lot of CPU and IO gathering stats when, well, that thing's going to disappear anyways. So that's one thing to avoid. There's plenty of others, but that might be outside the scope of this exact thing. I'm seeing a lot of things in the chat.
Yeah, I can read some of them to you. I can read some of them to you, Ryan. So
Sure.
is the plan cache created every time you run your SQLs, or is it just one time and gets deleted every time the IPL, as you said?
Yeah, so when your system boots up, SQE does a bunch of initialization. When it initializes, it creates the plan cache. So your plan cache is created once, and you can see this timestamp. So I'm on Common 7.5, one of Common's boxes, and you can see that we created the plan cache on September 4th. So this has existed for about a month now. Whenever you IPL, that plan cache goes away, so just created once per IPL cycle. But whenever you run a query, a plan is inserted into the plan cache if it has not already been run and cached. And we do prune plans from the plan cache. It gets a little complicated, but hopefully that answers the question.
I have another question for you. So for example, when someone goes to a doctor and they get some kind of, let's say a blood test, for example, they get this extensive report, and you try to look at this thing, and some of it makes some of it sense, some of it doesn't, but you really need a doctor to help you interpret that report and understand what's going on. Now, you talked about a certain couple of things already on this one screen, on the plan cache, but are there any things on here that you look at and just as what are your exact numbers, like where you can get a quick snapshot of what's going on in the system in 20 seconds or less? I mean, you mentioned a couple. Are those the ones that you look at specifically, or are there other ones that you use and you build a little model in your mind of what's going on in your system?
It's tough because normally I view it from the perspective, I guess for context, part of my job as a developer is to help triage customer problems. So if there's a bug in our code, or if there are significant performance problems with the query and some of our other support reps can't sort of rectify that problem, we get brought in to help. And this might look like a query rewrite or a new index that we provide to a customer. So it really depends on what problem we're facing. So it's a tough question to answer just from a broad scope, right? If we're seeing, for example, a really, really high memory footprint from SQE, right? You can look and see your memory usage with something like collection services. And if you see a lot of database memory usage, then maybe I will go to my plan cache size, right? Maybe I'll go to my temporary runtime object size and see that there. There's indexing strategy, right? There's this temporary index summary. So if your indexing strategy is really poor, maybe I might want to go look and see how many MTIs have been created. So those are system sort of maintained temporary indexes that are wiped away once you IPL. And if we have a lot of MTIs built, it's kind of a footprint that says, hey, your indexing strategy might not be as good as it possibly could be. And you might be letting performance sort of fall to the wayside there. Lots of other stuff. There's this query supervisor thing, which can help with long-running queries. There's all sorts of stuff to look at. But certainly this panel here is the high-level view of your system and of the plan cache and kind of SQE in general.
Okay. I mean, there's a lot of information on there. Is everything on there important to somebody at some point?
Absolutely. Yep. Very, very important to someone. In fact, most of these have come from requests from either customers or our own support team. In fact, this one here, time plan cache was last pruned, was added relatively recently because we wanted to see the last time a plan was removed, because a customer was saying that all of their plans were getting pruned really, really quick, repeatedly before they would reuse them multiple times. And we wanted to just verify if that was true. So that's in there, right? Lots of other stuff, but certainly every one of these is valuable to somebody. So Marius asked, what exactly gets cached in the plan cache? Is it just the SQL and its results, or is there some temp data also stored in single level store? Good question. And I'll click show statements here, and I'll let this run. There's quite a few plans in this plan cache, so this could take a little bit to come back, but it'll be nice to have for demos in a little bit. So you mentioned the SQL. So obviously the SQL statement itself is stored, but there's a lot of other stuff that gets stored. The results don't necessarily get stored, which is a little confusing. The plan cache essentially just contains the blueprints to run the query, not necessarily the results of the query itself. This is getting a little bit into the weeds here of the technical details, but maybe you folks like that. When you have a query that's been run multiple times, we will open a cursor. And well, technically a cursor is always opened, but it gets hard closed the first few times it's run. And then we do what's called a pseudo open, which is a cursor wasn't hard closed last time because we've run it a sufficient number of times. And at that point, we can actually start reusing the results from the previous run, provided the underlying data doesn't change. And that's the really, really big thing here. If you have tables that are constantly changing, we need to run the query again to get the most up-to-date data, right? But if you have, for example, a system where you pull off all of today's data and do a bunch of business analytics over it, if you're running a query many, many times against that data, chances are we're going to reuse those temporary objects as or sort of that result set as part of processing. If I scroll through here, actually, this might be a better way. If I look at all of the data made available, oh, that's kind of buggy. There we go. It just looks bad. I'll make that bigger. You can see that we store a bunch of runtime information too. And if you want more runtime information, please go make an idea. We know that this is really helpful, but there could be more stuff out there that some customers might want. But you can see like average processing time, average result set rows, average temp storage used, the optimization time, all sorts of things. So we store many, many metrics about the plan as well, about how it executed, the I/O and CPU stats, those types of things. And lots more that we don't show you that are only for internal use that we don't publicize, but hopefully that answers the question there. Henrik says it would be okay to lose the plan cache across OS upgrades. Thank you, Henrik. I agree. Thanks for making my job a little easier too. Stefan says, if you like, you can run a plan cache snapshot ahead of IPL to keep a copy. I would not like to keep fairly old stuff in memory forever. Agreed. And that's a really good point. And I'll show plan cache snapshots later in this presentation as well. And okay, Jose says that's the one we covered already, which was is the plan cache created every time you run your SQL. So, okay, I think we're caught up on questions there.
We are. So let's talk. So optimization. That's always a big, and we're in this area right now, and I think it would be fair to we have to bring up AQP at some point. I think that's in the same realm here, adaptive query processing, to help. I think to better optimize or to reuse things like that. What can you tell us about the AQP? Is that something that we can also better harness, or is it's just built in? It's already in there? Shed some light on AQP for us, please.
Yeah, so AQP is adaptive query processing, and essentially what it does is it's a secondary thread that runs alongside your query, provided that the query runs for at least 2 seconds. It's a little expensive to spin up this secondary thread, so we try to avoid doing that for really, really quick running queries. But there's no way that you can really target your usage. That doesn't exist. It just kind of does its work in the background and nudges optimization in the correct direction, or hopefully the correct direction based on what it sees. So it's not really possible for me to show you a ton about AQP via any of our tools. If you use Visual Explain, for example, it might show you if AQP has stepped in, but it won't really provide too many details. Database monitors will contain what record is it? 3023 maybe? I can't remember. That will tell you when AQP stepped in, if that's of interest. But in general, it's not something that I think most people need to investigate. Now, what AQP actually does is while it runs sort of secondarily to your main thread, it is analyzing the runtime of this query. The optimizer is estimate based. And I think I've said that. Actually, no, I've not said that yet today. I've said it in the podcast before, though. So it's estimate based. None of what we're working on is sort of based in reality unless we have an index built over it. And once again, any of these topics could be like a full hour, so I'll try to keep it short here. But when we see, actually, let's open up a query. Let's open up a visual explain diagram, and maybe we'll have some interesting queries. That thing is massive. Let's see if it has something fun. So when we have a table, if you have 1 billion rows in your table, and that's not uncommon for some larger customers, oh, this is all UDF, UDTF stuff. Okay, not a good one. I think this top one has some interesting things. So when you run a query, we need to understand roughly what is in your table. Man, I'm striking out here. That's all right. So what we do is we go and we randomly select 1,000 rows from all your tables, and we build a statistical model of your data. Of course, as your number of rows grows to larger and larger counts, like 1 billion, those 1,000 randomly selected rows, we don't change that number, and it gets to be relatively inaccurate. So this is all estimate based. To properly give statistics to the optimizer, we typically use indexes to build better statistics, and we also use AQP. So AQP will monitor the runtime of your query, and it does a few things. One, it inserts actual stats into the database or into SQE itself. What I mean by that is instead of having to rely on these estimates that we've sort of contrived before optimization, we are able to use real stats that we've collected from a query running to influence future optimizations, which is really powerful, right? It's like self-learning in a way. It's not machine learning. Let me make that clear. It is not machine learning at all, but it's sort of a self-correcting algorithm. The second thing it can do is it can change various runtime parts of your query. The first one is changing join orders, and we don't have to get too far into that today. That's a bit outside of the scope. But the other thing that we can do is we can enable SMP, and that was actually a 7.5 addition. And if I go back to the plan cache properties, the main screen here, there's actually this row, and it's total number of queries with runtime adjusted SMP degree. And notice that we're not really building any SMP queries on this box because, well, this is just like a sandbox for people to play around with. They don't really care about their performance. But if you enable SMP with 7.5, automatically AQP determines whether or not SMP should be used, which we've seen provides a significantly better performance footprint for queries as compared to enabling SMP for everything. But yeah, AQP is certainly a cornerstone of our sort of technologies and will continue to be into the future. And we're always looking at ways to improve it.
Right. I was hoping you could bring up a visual explain because I think that's one of the important tools in our tool set to help us build better queries, or at least to understand what the queries are doing, and maybe I think to improve them as well. Is there one that you might be able to find that might even if it has a UDTF in there or a UDF, and I think that would be okay. I think.
Yeah, let's do this one. I have some demos from previous presentations I've given on this system. I have one in mind that's quite a good example.
Okay.
Let's see if I can find it. It's I believe it's this one here. So you can generate a visual explain from many different ways. It can be from run SQL scripts. It could be from a plain cache snapshot, just like this. And I'll start generating this one. And the idea is that visual explain allows you to look at the actual plan determined by the optimizer. And in that way, you can sort of maybe change your data model. You can change your indexing strategy, change your query itself, or understand the performance characteristics of the query. So this is a nice example for a few reasons. First, when you run a visual explain from a plan cache snapshot, we aggregate a ton of data across all of the runs that you ran with that query. You can see that we ran this specific query for 10,000 milliseconds. So not a super long time, but on average, it was that 10,000. We really ran it for 9 times for a total of 92,000 milliseconds. And there's some other high level pieces of information. Make that a little bigger for you as well. This can be really useful for determining if you have certain performance problems or characteristics. This is a really nice way to look for them. For example, if you see that your disks are pinned to like 99% read activity, right? They are exhausted. They can't really keep up. You might want to look for queries with a lot of database reads. So these are synchronous and asynchronous database reads. Could be something good to look for. Page faults, you can't really do a whole lot about that. That's relatively sort of under the covers, but there are a few things you can change, which I actually highlighted on Charlie's iChime at Navigate. So I'll leave that tip there. So try to lure you to the other thing I did with Charlie. There's also temporary storage use. So if you're seeing problems with tons of memory being used by your queries, you can see how much memory was being used. Okay, awesome. So that's high level stuff, but what if I want to dig in? And this example I think is really nice because it's this big nasty query, right? And in fact, I can open it up in a run SQL scripts window and I can format it. Oh, it does this sometimes. Lame. Okay, sometimes our formatter has problems where, yeah, get rid of you. There we go. Beautiful. So it's some big nasty query, right? How do I know what's a problem if this is performing poorly, right? Is it a problem? Well, that's sort of a different conversation, but let's say this is a problem, right? This is a problem query for us. How do I investigate it to figure out how that would be sort of done? Well, the first thing I look for is are indexes being used properly? And when I see this query, there's a lot of different predicates here, lots of ands, lots of things to test for. And I'm immediately going to look for these table scans. And for those unfamiliar, a table scan is when we look at a table and we go from the first row to the last row to try to look for a certain value. So if I click on the table scan, if I scroll all the way down, you can actually see sort of the SQL statement text for this node. And I'm just taking some data, the key field, the timestamp, a character field from this table. Not a whole lot going on. On this other table scan, I'm also taking a little bit of data, but I do have a where clause here. Actually, quite a ridiculous where clause, right? So immediately I'm looking at this one and saying, okay, we have a lot of work being done. What you can do is if you scroll to the top here, we have the total number of rows selected and processed. And processed means we looked at this row, and selected means we looked at this row and we're feeding it back up to the node above it, right? So we're passing it through the node. It meets our criteria for what we're looking for. If we look at, if we look at this one, we see that we're doing a total of 50,000 rows. Not too bad. If we go to this right-hand table, we see that we're doing 2.46 times 10 to the 9th rows. Quite a bit more data, right? A significantly higher portion of data. And out of those, we're only selecting about 104,000. Really, really low amount of data compared to the total number of rows we're looking at. That number of selected versus processed is actually called selectivity. So the percent of the data that we're taking out of the table. And this is a really important feature of database tuning. Essentially, I look at that and I say, if it's a really, really low amount of data, I know that I want an index over that data. So in this case, I actually have, where is it? View. Highlighting. I have highlighting turned on in my visual explain sort of view. The one that I have turned on is index advised. And that says, show me in this nice blue color, what tables have indexes advised for them. And the way I can actually look at this is I can do actions and then index and stats advisor. And you can see here that the system has actually recommended we build indexes for both tables. Interesting. So how do I know which ones should I build? Should I build all 6 indexes? The answer is no, by the way. I'm not going to let you entertain that thought for too long. The index advisor essentially works on the basis of not being able to try a certain strategy. So what happens is the optimizer wants to look at a certain approach or method for gathering the data, but it can't even cost it or it can't optimize for it because the index doesn't exist. If that index did exist, it doesn't necessarily mean that strategy would be faster or more efficient. It just means we'd be able to try it. So by that sort of fact, it means that index advisor entries aren't simply for making your performance better. It's to allow the optimizer to have more options. More options aren't necessarily always better because more options might not even be used, right? We might consider them and they're slow. So in this case, how do I know which one to create? And basically the idea here is that if I look at the top, we have this estimated time, right? So if I go back to this left-hand side, reminder that it's only querying 50,000 rows, we're estimating the processing time to be pretty small, 134 milliseconds. So very, very fast. If I go to the right-hand side table, that is 283,000 seconds, or sorry, milliseconds. So much, much more data. And yeah, that is a comma there. I'll make that bigger. That's a comma. That's out of the screen now. This is a disaster. No, it's really not, but there we go. So 283,574. So this one is going to cost much, much more. Combined with the fact that it's going to cost a lot, and we have a low selectivity, which low selectivity table scans or operations are generally favorable for using an index, generally beneath 20% or so. This is the index I'd want to build, or this is the table I'd wish to build indexes on. To see those specific ones, I can actually right-click the table itself and say advise indexes, and it will filter down just to those. From here, I know that I want to build an index, but it gives me 3. It's then up to the programmer to decide which ones to build. And of course, that's a bit of an art form as well, because indexes can be used for selection. So that's both the select list and your where clause. They can also be used for ordering and grouping. So determining the optimal index is probably outside of the sort of topic of discussion today, but it's a really, really important sort of thing to understand.
I have a question for you, Ryan. So you mentioned that as far as advised indexes are concerned, you talked about this percent selectivity, and you said you had 4 in this example, and you said 20 or below is generally as a one number you use to actually create another index. But in my mind, at least, I would have thought any number, or in fact, I would have thought just the opposite. I would have thought even a higher number would really benefit us if we had a lot of activity on that search criteria and having an index built, in that it would have performed better across all queries. What am I missing here?
Sure. So 2 things, and it's not a prescriptive rule. 20% can certainly be broken, and we do see that in some cases. Sometimes we might even see when there's 100% selectivity, an index will be used. It just depends on what the query is asking for. The big thing to keep in mind here is that while an index is faster to access than a table, the index is a structure that does not necessarily contain all the data required. So what I mean by that is if you do a select star from a table and you have a where clause that says, where key equals 1, for example, right? We're going to go and get 1 row from that table. But that requires us to first go and look at the index. And we essentially interrogate the index and say, go down this structure and find all the rows with the key being equal to 1. So that's a fast operation, but it's not necessarily free. And the big picture here is that there is a crossover point where needing to go and touch the index repeatedly is doing a significantly greater number of I/O operations than are really required for optimal performance. So if we have 50% of the data that we are looking for fulfilled by some predicates, and we're asking the index, every time we ask the index, we still have to go back to the table and get the data anyways. And when we do this, we're sort of jumping around a lot, right? We're going from an index and it gives us a address in memory. So we get a row number and we can calculate the address from that. But we jump over to the table from there. The problem is that we're doing a lot of I/O activity and it can be really slow. And in fact, at that point, if we just iterate through the table row by row, it's actually going to be faster just to do the work. When we, like I said, have roughly less than 20% of the rows. That can be broken. There's this thing called index-only access, which is when your index satisfies all of the data being returned in your select list and the selection and ordering and grouping. Well, not necessarily selection and grouping, but it can be the case too. And we never have to touch the table at all, in which case you might see an index used for much higher selectivities like 80, 90, 100%. But those are more specific cases, and oftentimes it's not really what we see in the field unless someone has some really, really strong indexes built. Does that hopefully make more sense?
It does. Let's keep on this index because I know indexes are in my discussion with a lot of developers, that seems to be an area that a lot of people tend to drift towards. So let's go back to even the Index Advisor, for example. And if you can open it up, maybe Index Advisor, you can see, you'll know that it has number of times this path could have been used had an index been available. For example, like one of the columns has a number in there. Am I looking?
Not on this screen.
No, on Index Advisor itself.
Are you saying like the actual underlying table?
Yes. And if you can sort down that table and you can easily see which ones are being used over or should be used over and over again.
Let me think. Let me reconnect. The best way I know how to get to that, I know ACS has a panel somewhere to look at that, and it's really escaping me where that is. But there is
It'd be in the view
QSys, from QSys2.sysidx ADV. Oh, I'm getting the name wrong. Let's prompts here. It might even be QSys, not QSys2. Oh, I saw it. It says IX ADV. Okay. I don't know why we deviated from.
And just to tell everybody how you got that window to pop up, what function key? What did you press to do that?
That was F4 in my case.
Yeah. Okay.
I think some folks might have command space or Windows key space. Yeah, control space. But for me, it's F4. So for those that don't know, all of the index advice is actually pulled from this table here. So like Charlie said, there's this times advised column. So I can just write a query to look at this. I don't have to use ACS or anything. And we'll go descending. And of course, that'll spin for a little bit, but you can see this index has been advised 11 million times. So it's a lot. Once again, it doesn't necessarily mean that this index is going to be super beneficial for performance. It just means that we have sort of wanted to try a strategy involving this index 11 million times, and then we have updated this piece of information. And you can see all sorts of different stuff here. One of the important things is like table size, right? So this is, I don't know if the size is in bytes or megabytes or what it is, but relative to some of these other table sizes, well, certainly this is not going to be megabytes in this case. I'm going to guess it's bytes. It's a 99 byte table. Probably not worth building an index over a 99 byte table. That's just very, very, very small. You can see that an MTI was created for that advised index as well. So that's, once again, the optimizer sees a sufficient need to create the index, and so it goes ahead and does it. It's a stronger signal that you should build the index, but not always. And in fact, sometimes MTIs are required to fulfill certain requirements about the request. Like, for example, there's a option you can put in your INI file, your QAQQ INI file, called allow copy data, which basically says, are we allowed to copy data into a temporary structure to sort it, group it, that sort of thing. And some folks need live data. And by that, I mean, if we were to copy data into a table, we're actually not fully live yet because we're operating off of that sort of cached data, even if it's only for a few milliseconds. So in that case, MTIs are forced to be built if an index doesn't satisfy that ordering or grouping requirement already. There's lots of other stuff here. Like this thing was first advised in 2018. Kind of an interesting piece of information, right? If it's gone and performed well for, what is that, 6 years, 6.5 years, it's probably still fine. Lots and lots of stuff in this table.
So Ryan, are there any on here that jump out at you to say, oh, oh gosh, we really should have an index created, based on what I'm looking at this table, at this information right here, at this result set?
Yeah, let's see. So,
and I'd be curious to how you got to that conclusion also.
Yeah, and I'd have to look at the plan itself as well. It's difficult to tell without the plan. In general, the number of times it's advised is an indicator of how often that query is being run, which is a useful thing. If you have an advised index that is only advised once, it's probably not very useful to build the index because indexes have cost associated with them, right? We need to update them as the underlying data updates. So I still want to see these frequently requested indexes up top. I'd probably want to see larger table sizes, as well as lots of MTI usages and like a recent MTI creation date. In fact, this one was created today, which is quite funny. But like, for example, this one right here, there was an MTI created, actually that timestamp must be not Central Time because it's 2:11 here in Central Time, and this is 2:24. So that's in the future. Must be East Coast time or something. But I'm seeing, 222,000 bytes. Once again, still not big, but relative to the rest of my, this is MTI used. That's actually a pretty significant number of MTIs used. That's actually used 2 million times, excuse me, but a small table size. So maybe not that one. If we scroll down, we're seeing some bigger table sizes here, certainly, and also lots of MTIs used. And in fact, this one might be the winner so far out of all the entries I've seen without seeing the plan. Once again, I kind of have to see the plan, but it's a big enough table where that might be interesting. I can see that the MTI was used a lot. So it means even after we built that maintain temporary index, we were still using it a lot. And what we can actually do is MTI used, let's scroll over. And I'll check sort of the name of the table. And in this case, I immediately know that an index would not be useful. This is a collection services table. And that's like an operating system table that you're not really supposed to build an index over. In fact, I recently helped the collection services team identify performance problems with their things. So maybe this will get fixed in a future PTF. So that's kind of funny.
Right.
But
maybe this wasn't a fair table to be looking at to begin with. I mean, maybe if it's not a traditional transaction table in my ERP.
Yep. So for example, I'm just going to filter out all schemas starting with Q, right? Get rid of all of my system libraries. And this will take a little bit to run as well, now that we're actually doing some filtering, but this would get me a little closer. So this looks like someone's user profile.
Here we go.
Kind of interesting. And they have a bunch of keys. Once again, still a lot of advised indexes. Pretty small table sizes, but not, insignificant compared to what we were seeing. And you can kind of see the formula I'm using here, right? I'm trying to identify large data sets that are frequently being used. And from there, what I would probably want to do is go and look at queries that were using the table. So let's say, for example, I think this table, this XAGWU table is interesting, and it's in this lab test. How can I possibly go figure out what queries are running against it? And I'll use this to show you how you can take a plan cache snapshot. And plan cache snapshots allow us to capture everything within our plan cache. So that's all plans. Or I can do it for specific different metrics or objects or queries. For example, I could say, give me the top 25 most frequently run queries on my system. That's nice. I can do the same thing with accumulated runtime, overall runs, temporary storage, that's memory usage, CPU usage, and reads. So kind of your big performance characteristics that you'll want to be looking at. But if you come down here to the bottom, statements that reference the following objects. I can add, so let's go back and let's do lab test. I'll just bring it over here. Lab test and XAGWU. And I'll hit OK. And now I will scrape the plan cache for all plans using this object. Now, okay, I need to give it a name. That seems fair to me. Let's call it, Charlie Demo. How fun is that? So this will go ahead and run. Based on how large your plan cache is, this might be really quick. In fact, that was shockingly quick. This could also run for hours. I have seen people with 100 million plans in their plan cache. That is a lot of data to get through. So this analysis can take a good bit. So let's go see if it captured anything. My guess is going to be no. That was a pretty old table. And it'll spin for a little bit and nothing, which is unfortunate. But if we go grab one that had a more recent date on it, first advised, oh, they're all quite old. That's unfortunate. This is a pretty inactive system. This is what you'd expect. But hopefully this would give you a picture of how you might go and analyze this, right? Look at your index advisor, figure out what indexes are really sort of in demand. And then from there, you can dig deeper into the query itself using Visual Explain. You always have to understand sort of the big picture, which is your overall environments and what pain points you might be having, as well as focus down sort of towards a more narrow view on the individual query itself. Both are really important to sort of guarantee well-performing queries and a well-maintained database.
So these are for creating indexes to get better performance, better productivity out of the system in general. Yep. Once I create an index, be it with DDL or just do it directly from Index Advisor, which I know you can do as well, how soon can I start expecting to get a performance boost? I've created an index. Well, then the next query will pick it up or attempt to.
Yep. Yeah, so that's a great question. The next query will certainly use it. What happens during optimization is once we store that plan in the plan cache, when we go to run that query again, as we check the plan cache, we look for so many different metrics to prompt us to re-optimize. This could be something as simple as the table has changed size. And in our case, it's a 10% change in size. So if your table goes from 1 gig to 1.5 gigs, we will actually say, hey, go re-optimize because the data's changed significantly. We might have a better plan available. And then it'll go out and re-optimize. This will also happen for new indexes. So we'll check for new indexes against all of the tables that you're querying. And if there is a new index, we will also go and re-optimize. This is really, really useful because, yeah, if you have a ton of queries running some bad plan, you want to kick them out and get them using that new plan as soon as possible. And that's a really, really easy way to do it, is just have the system do it for you with a new index.
Well, if we're going to stay on indexes, because that's such an important point, let's go a little bit deeper and talk about EVTs or normal indexes, and why would you use one versus the other, and what is the difference?
Sure. So EVIs are encoded vector indexes. And I wish I had a little chart for you guys, because it'd be fun. No worries.
Yeah.
So a radix index is, I wish I had like a paint, and I'm on a Mac, so I don't have paint. That's unfortunate, but that's okay. So a radix index is a binary tree. And essentially what it does, you can think of it as a series of sort of substrings of your value. And we go down this tree structure and we test the thing that we're looking for compared to the current value of the node in the tree. And as we go left, right, and down and that sort of thing, eventually we end up to a leaf node on the tree. And what that leaf node contains is a list of row numbers that satisfy that requirement. So if I build an index over a primary key, for example, What will happen is I will go down that structure. And of course, I'll find either 1 or 0 rows on that leaf node, right? Because it's a primary key. We're enforcing uniqueness there. Very, very important sort of concept of the binary radix index is that it's ordered. That tree structure is a ordered structure. And we don't have to get too far into exactly how it's ordered unless folks are curious, but it's ordered. So what this means is that we can use it to satisfy different queries that do ordering or grouping. A EVI is a different type of index, and it has 2 different parts to it. It has what's called a symbol table and then a vector. The symbol table essentially contains a value for every unique value in your table. A pretty classic example of an EVI usage is for a states column in an orders table. EVIs generally excel when the cardinality is pretty low. The reason this is that there's 50 states, right? Well, plus or minus a few territories, that sort of thing, in the US. For every unique state that we see, we will add an entry to the symbol table. And the symbol table contains a few different things. One, it contains a unique code for every unique entry. It also contains a set of aggregations that are pre-calculated for that entry. By default, it's just a count. So by default, we know how many of a certain value exists in your table, which is really, really useful. You can also specify an EVI to be created with different aggregations built in. So averages is one, sums are other. It's mostly mathematical operations. The benefit there is if you're doing a lot of analytical calculations against your data, instead of having to actually calculate that average or that max or whatever it is against your data, instead, all we need to do is just ask the index, and the index has it pre-calculated for us. This, of course, means that we need to calculate this new aggregation every time the data is updated, so it gets expensive, but for certain queries, it's really beneficial. EVIs, I should note, are not ordered. They're not an ordered structure, so they cannot satisfy ordering queries. They can do grouping, but not ordering. The second part of this EVI structure is this vector, and it's actually how it works in practice, which is when we use the EVI, we consult the table, and let's say we're looking for states in an orders table, right? And we're going to look for Minnesota. Minnesota is going to have some unique code associated with it. Let's say it's code 40. What will happen is we will consult the vector, and the vector is actually containing a value for every row in your table. And all we do is we scan that vector and we say, find all rows that have, or all values that are 40, right? Matching our Minnesota selection. This is way faster than looking at the table because these codes are really small. They actually change size. There's 1, 2, and 4 byte codes, depending on how many unique values you have. But it's much, much faster than navigating through the table itself. So we can scan this vector so fast compared to a table. And from there, we get either a list of relative row numbers or a bitmap, a series of zeros and ones that either say 1 is select this row or 0 is don't select the row. Those are used in different scenarios when the optimizer thinks one is more beneficial than the other. But in general, sort of the big picture is that an EVI is really, really fast for certain kinds of selection and grouping. In almost all other cases, a binary radix index is going to be a better general purpose fit, but is definitely not the only thing you should be building. An EVI is certainly useful.
Right. And the metric I've always been given for an EVI is if you're going to do that, use it for, and you've said it already, use it for something that you have to know your table. You have to know what's in the table and use your best judgment as to if you have a key value that's in every other row, that may not be a good candidate for an EVI, maybe one where it's less frequently. That's how I was taught how to use EVIs.
Yep. Yeah, you certainly need, I think EVIs are a much more in-depth and complicated index to use. You certainly need to understand what your data looks like. The cardinality or the unique number of values per column is very important to know. You need to understand how the queries are using it, right? If you're typically using these queries that use a lot of ordering and your indexes typically satisfy that ordering, and EVI isn't a good fit there. So it's certainly a much more targeted approach for an indexing strategy, but it can be really, really fast in some cases. In fact, one of the motivations for building EVIs was to enable EVI only access, which is some pretty crazy stuff where if you build an EVI over every single column in your table, we never actually have to touch the table. We only touch the indexes for every single query that ever touches the table. Super, super fast. Almost nobody uses it because it's really expensive, right? Tons and tons of memory needs to be used for that. But if you have a huge system, huge partition, it's really fast. Anyways, that's enough going off into the weeds with EVIs, but hopefully that was a little fun.
Interesting. So we're actually we're kind of sort of coming already to the end because that's how these things always go. Can we touch upon a little bit about UDFs and UDTFs?
Yeah, I know we had that in the agenda. Let me really quickly open one. I guess, what would we like to know about UDFs, UDTFs? There's a whole world out there. I could talk about, actually, I have a few things I want to touch. We've got a few minutes. I want to touch on some of the topics we've already talked about in the context of UDFs, which is like performance and things we like to see and don't like to see, and then maybe a little bit about writing them, if that's fine. So one of the things I want to talk about is a query that might use a UDF. So let's say I have a query like select star from our molar.my table. Actually, let's go to a system where I know I have data available. And let's do UT52P6. We're going to go to a development system. As you can see, we have a lot of partitions. And let me get to this guy. I want to show you a real example of how this might work. And let's do select star from star1g to item fact. This is a table that we use all the time just for internal testing. It's like a 1 GB table. If you have a UDF in your select list, so I'm not going to use UDF here. I don't have any ones off the top of my head that I would know would work for this case, but let's just do order key, part key, and let's do something like, profit with tax, right? We're going to select a few fields. Oftentimes we will see UDFs in the select list here. So let's just say like my UDF, and we're going to feed in the profit with tax. From a performance standpoint, this is totally fine. What is not fine is if I have this exact same query and I add a where clause to it, and I say where my UDF is equal to 1 or anything. Having a UDF in your where clause is a massive no-no, super, super huge no-no. And you might be thinking, well, why is that? Why is that bad for performance? The reason is that this UDF is essentially a black box to the optimizer. We have no clue what's going on in there. You could be adding two numbers together, pretty simple. You could be making an API call to an external service and returning data, right? The complexity of that UDTF is completely unknown, and we have no idea what's going to come back. So when we're making our estimates in the optimizer, we want to understand what percentage of data is going to meet this equals 1 predicate. And of course, we have no clue what this is going to return. So we have no clue what percentage is going to equal 1. So we have to give a default guess of 10%. Generally, this is a pretty awful guess, right? We could be good, could be bad, but generally it's really awful. What we will see then is suboptimal performance from a plan. You might get lucky. We have customers that come in with performance complaints, and they'll say, hey, this was working fine for 10 years, and we updated to a new version of IBM. We're on 7.5 now, and it's failing. It's like, well, actually, we updated our optimizer, and we're now slipping into a slightly different plan, and we're now performing much worse because this makes that query vulnerable, right? We just cannot understand what your query is asking for, and so our optimization is not going to be very accurate. That's definitely one sort of way to do it. I want to open up, I have another file here, and it should be in somewhere in here, SQL scripts. And I have a UDF here. Let's copy this one out. I want to talk a bit about deterministic UDFs, which is another nice performance gain. Part of me doesn't want to just like rant on and on about how to create UDFs because I can't teach you much in an hour, much less, a day. But maybe some nice tips like this could help. A really, really cool feature of the optimizer is that we can cache the results of UDFs in the query if we can guarantee that a given input will result in a given output. So let's actually do this. Let's create this function, and it will go ahead and create it for me. And let's call that, so det UDF. Oh, well, that'll fail. My UDF I forgot to get rid of. That's a bummer. All right, let's go back and run that. This should work just fine. And this is obviously junk inside here, but the main thing is it returns the same value for the same input. And in fact, if I go and do a visual explain on this, this will spin for a little bit. This is a pretty old partition running an older version of the operating system, so certainly not going to be fast to pull this up. But the main points here is I'm declaring this function as deterministic and as fenced. Deterministic tells the optimizer exactly what I've been saying a few times here, which is for an input, let's say I always put in 1, I'll always get out some other value. And what this allows us to do is cache away the results. And this is actually pretty awesome. You can see that I'm feeding in 6 million rows. And what's happening is this cache probe, instead of calling this UDTF over and over and over, or sorry, UDF, we're actually just going to call it only a few times. And this is estimated, of course. I could get an actual runtime, and this estimate's a little off, to be honest. But the big idea here is instead of running that UDF 6 million times, I'm going to run it maybe a few hundred times. If your UDF is complicated, like it's adding a bunch of stuff together, it's running a subquery, it's doing something, eliminating extra runs of that UDF can be a massive performance gain. I've done some really simple tests where I've taken UDFs from customers and made them deterministic and fenced. Fence is just required to get them to be cached like that. It's like a 20% improvement in performance for essentially free. And that's a pretty easy case. I could easily see a scenario where someone might improve the performance of a query by thousands of percent just by doing this. So that's another fun little tip.
And I'm just going to interrupt you for a second. That would be best used if when you always know that when I pass ABC, I get 1, 2, 3 back for you. You have to, when you have a known result every single time.
Correct. Yep. If you apply a deterministic and fenced sort of keywords to a function that does not always return ABC for 1, 2, 3, you're actually going to get incorrect results out. So you have to be 100% sure that you are always going to return the same value. If that's the case, you can see, awesome performance gains.
Excellent. Lots of good stuff.
I see a few more questions here in the chat if I can answer those, I suppose.
Sure, absolutely.
Sure. So let's see. Jose says, Ryan, there is no way to see the plan cache of an embedded SQL unless you run the piece of SQL in ACS. No, that's not true. So every query that is run using SQE will be cached in the plan cache. So even if it's embedded SQL in your RPG program or a C program or Java or whatever it is, it will always be in the plan cache if it's running with SQE. So ACS is certainly one way to run a query, but if it's your application running it, it will show up there. Marius says, is there a way to check in the SQL plan cache of how many jobs did a SQL statement use in a time frame? If I go back to that, there's not a number of jobs that would use it, unfortunately, but there is a number of times it was used in general. Not the same thing, right? But the plan cache and SQE doesn't really care what job is running it necessarily. It just cares that a request came down, right? Many jobs can share the same query. So you can see here, total times run is a column available, but no, the jobs themselves are not made available. I will provide my email in the chat here for everybody. So if you want to email me a question, um, feel free to send me one after this. I'd be happy to respond to you. If you've got really huge questions in terms of like things about your environments, your queries, that sort of thing, probably outside of the scope of what I'm able to provide, that would be more of like an expert labs offering. So an offering where they'd help you out there. But if you've got some questions about SQL or some queries you're trying to write or procedures, functions you're trying to write, or just some brief performance things, yeah, I'd be very happy to help.